hexose was attained after positive glyceraldehyde underwent 3 successive Kiliani Fischer syntheses. Identify the hexose from the following experimental information. Alright, so my final product over here, the glyceraldehyde, that positive just tells me I have D-glyceraldehyde, right? So I have my aldehyde here, I have the CH2OH, and this is an OH, that's an H. At the beginning, I had a hexose. Now that's a CH2OH, and since it was D-glyceraldehyde that we started with, we know this is a D sugar. So that's all we know about the starting reagent so far. Hexose, OH on the right, giving us a D sugar. Alright, our first little reaction we introduced was doing that oxidation with nitric acid. If you don't remember, that's going to make carboxylic acids out of both ends. That's still OH. And let's see, does it tell us anything useful about the other 4 positions? Normally, might tell us about one. But it forms an optically active aldaric acid. That really doesn't help because if it was optically inactive, I'd know this is an OH here because it has to be mirrored on the top and bottom. But inactive, it could be here or here because it's the other 2 locations might interact with it. So I can't do anything with that yet. So I'm going to be coming back to that one. All right, I do a Wohl degradation of the original aldohexose, followed by oxidation. That's going to rip that top end off. And then after the oxidation is going to make it a carboxylic acid. And we have an OH there. But that one forms optically inactive. All right, because it's inactive, I know that location is OH. Because that would mirror the top and bottom. It wouldn't matter what that middle location is, because that's right along that plane. All right, since I know that here. And I know that here. All right, I can't do anything more with this yet. Because one of these 2 just needs to be opposite, and that would make it optically inactive. All right, so what's my final thing? If I do a second Wohl degradation, probably from this middle thing, I get erythrose. All right, that finishes this up. So erythrose is, OHs are both on the same side. So that tells us this location was OH, and this location was OH, and this location is OH. And now this middle one here, this guy we can figure out. Since it was optically active, I can't have the OH here, because if it was, it would be optically inactive. Therefore, the OH needs to be on this side. That's going to give us our final product, or the hexose in question. 1 OH on the left, the other 3 on the right.